As you rest here, letting your thoughts drift, consider this simple question. If the universe were not entirely real in the way we assume, would we even notice? Now, some physicists believe they may have resolved a paradox that has puzzled us for 50 years. But have they truly done so? And what other strange paradoxes challenge our understanding of the universe? Many people are already familiar with the Fermi paradox, named after the Italian physicist Enrico Fermi, best known for building the first nuclear reactor. This paradox poses a deceptively simple question. Where is everybody? Given that our star and our planet belong to a relatively young planetary system compared with the immense age of the universe, and given that it seems entirely plausible for a civilization to develop interstellar travel within that span of time, it feels as though we should have encountered some form of extraterrestrial intelligence by now. Some argue that it is not a true paradox at all, because we cannot be certain that intelligent life exists elsewhere. Yet the Drake equation is often invoked in discussions of this puzzle. This equation uses 7 variables to estimate how many detectable civilizations might exist in the Milky Way. When it was first proposed in 1961, it suggested the possibility of millions of Earth-like worlds hosting civilizations. At the time, however, we had no evidence of planets orbiting stars beyond our own. That situation changed dramatically in recent years. In 2020, astronomers analyzing data from the Kepler Space Telescope concluded that there are more than 300 million worlds with conditions similar to Earth spread throughout the Milky Way. Their findings indicated that roughly half of the galaxy's sun-like stars possess rocky planets within habitable zones, regions where liquid water could exist on the surface. Planets, it turns out, are astonishingly common, and they actually outnumber the stars themselves. Soon, the James Webb Space Telescope will venture into space to search for potentially habitable worlds in even greater detail. With this expanding knowledge, the question becomes more pressing than ever. If advanced civilizations are possible, why does the universe appear so quiet? Perhaps the answer lies just ahead as our technology improves, or perhaps contact has already occurred unnoticed. Recent unexplained sightings have fueled speculation that extraterrestrial visitors may already be here. Clear evidence of that would finally dissolve this paradox. Another curious puzzle is the bootstrap paradox, a time travel conundrum that asks how something taken from the future and placed in the past could ever originate at all. It is a favorite device in science fiction, inspiring stories in films and series such as Bill and Ted, Terminator, and Doctor Who. Imagine this scenario. You are a time traveler. Before embarking on your journey, you buy a copy of Hamlet from a bookshop. You then travel back to London in the Elizabethan era and hand the book to William Shakespeare. He copies it and presents it as his own work. Centuries pass, the play is printed and reproduced countless times, and eventually one copy finds its way back into the same bookstore where you first bought it. The question is unavoidable. Who actually wrote Hamlet? Closely related is the grandfather paradox. Once again, you travel back in time, this time to erase your grandfather from history. Returning to the present, you are faced with a contradiction. Without your grandfather, your father would never have been born, and neither would you. Your entire existence, your memories, relationships, and possessions would vanish. If you were never born, you could not have traveled back in time to begin with. Some physicists suggest that such an action might instead create an alternate timeline, or even a parallel universe. A common variation of this idea imagines traveling back in time to eliminate Hitler in an attempt to prevent the Second World War. This would lead to some fascinating consequences. Imagine you possess a gleaming time machine and a clear intention to journey back before events spiral out of control during a war, hoping to set things right. The difficulty is that the very act of intervening would erase the reason for making the journey in the first place, along with any knowledge that such a reason ever existed. Acting as a time-traveling executioner simply gives rise to a paradox. When combined with the idea of many worlds traveling into the past, might generate an entirely new timeline without difficulty, while the original timeline continues to exist alongside it. You could even create a new branch of history that turns out to be far worse. But then we can ask a subtler question. What might occur if you sent an object back through a wormhole? Consider what is known as the red sky paradox. Among all the stars in the Milky Way, 80% are red dwarfs, also known as M-type stars, which according to scientific calculations may continue shining for trillions of years. By comparison, the Sun will burn for about 5 billion years. It is therefore no surprise that red dwarf stars are far more numerous than any other type. With so many red dwarfs out there, our night sky ought to be dominated by their light, and at least some of them should host planets suitable for living organisms. So where are all these red dwarfs, and why have we not yet found life in their systems? The way we observe stars in space is very different from how they would appear through Earth's atmosphere. Seen from space, the sun appears white, massive, and extremely hot stars glow with a bluish hue, and cooler stars appear white or orange. Red dwarfs are so faint that even the nearest one, Proxima Centauri, cannot be seen with the naked eye. In telescope images, such stars can display different colors depending on the filters used. But the red sky paradox has nothing to do with the color of the universe itself. It is really about the search for alien life. The central idea is that planets orbiting red dwarf stars should have the best chances for life to emerge. These stars live far longer than stars like our Sun, and there are vast numbers of them. About 15% of red dwarf stars have Earth-sized rocky planets orbiting them. Most of these exoplanets lie very close to their stars, meaning they receive plenty of light and heat conditions that could allow liquid water to exist on their surfaces. And yet life, as we know it, thrives only on Earth, which orbits a yellow dwarf star. Yellow dwarfs, however, make up only a few percent of the stars in our galaxy. Does that mean our star is somehow special? Not necessarily. The Copernican principle tells us that there are no privileged or special places in the universe. In that sense, our location is ordinary. But that does not mean life itself is common everywhere. There may be explanations for this apparent paradox. Red dwarfs could be far more dangerous to nearby planets, bathing them in intense and deadly radiation. Their strong gravitational pull can also cause close planets to become tidally locked, leaving one side scorched and hellish while the other remains frozen and dark. Planets in red dwarf systems may also lack protection from objects arriving from deep space. If you search the NASA catalogue for gas giants near red dwarf stars, you will find they are extremely rare. Giant planets like Jupiter often act as a kind of cosmic shield, interacting with comets and asteroids that might otherwise devastate rocky worlds. Taken together, these factors make life roughly 100 times less likely to arise in red dwarf systems than around yellow dwarf stars. Space is filled with remarkable stars, and one idea challenges our conventional understanding of reality. A famous thought experiment describes a billiard ball sent through a wormhole that allows travel into the past. In this scenario, the ball is fired into the wormhole at a precise angle. If it continues unaltered, it will emerge in the past at exactly the right moment and direction to collide with its earlier self, knocking it off course and preventing it from entering the wormhole at all. That seems to generate a contradiction, yet clever solutions exist. The ball could emerge from the future at a slightly different angle, delivering only a glancing blow to its younger self. Rather than stopping it completely, the impact nudges it just enough to alter its path, so that it still enters the wormhole at the angle required to make the entire sequence self-consistent. If I could offer a quiet word to a younger version of myself, it might be this. There are moments in science that gently strike your understanding of reality, not with force, but with a glancing blow that lingers. One such moment comes from what we call the paradox of the oldest star. There is a star known as HD 140283 resting in the constellation of Libra, roughly 190 light-years away from Earth. Astronomers first began to uncover its story when they used the Hipparcos telescope to track its motion through space. They measured its speed at around 1.3 million kilometers per hour, yet it was not the velocity that caused raised eyebrows. It was the age. Early estimates suggested this ancient object was about 16 billion years old, a deeply unsettling result when set against the age of the universe itself, which we understand to be only 13.8 billion years old. Faced with this contradiction, scientists chose to look again more carefully, more patiently. After 8 years of further investigation, aided by the Hubble telescope, they employed parallax measurements, spectroscopy, photometry, and detailed studies of stellar brightness. From this richer data, they concluded that HD 140283 is closer to 14.5 billion years old. Even so, measuring distance and luminosity with absolute precision is extraordinarily difficult, leaving an uncertainty of around 800 million years. That means the star could be as young as 13.7 billion years old, slightly younger than the universe itself, though only just. And yet, when we turn our attention to phenomena much closer to home, the puzzles become no less profound. Consider the observer's paradox, something genuinely unsettling. Among all the strange consequences of quantum theory, few are as famously disturbing as Schrödinger's tale of a cat that is neither alive nor dead. To be clear, this is purely a thought experiment. No animals were ever harmed. The scenario imagines a cat sealed inside a box with no windows alongside a small amount of radioactive material, a Geiger counter, a hammer, and a vial of lethal poison. The radioactive substance has a 50% chance to decay. If the Geiger counter detects a particle, it activates the hammer, which shatters the vial, releasing poison that would kill the cat. Until the box is opened, there is no way to know the outcome. And so according to the mathematics of quantum mechanics, the cat exists in a state of being both alive and dead at the same time. It sounds absurd, and yet it arises naturally from the theory. The strange implication is that the act of observation itself influences reality. You cannot confirm that something has happened until you observe it. This may all seem deeply unsettling, but it leads us naturally to another observer's paradox, the famous double-slit experiment, perhaps the most iconic experiment in the history of physics. Imagine a wall with two narrow slits and you throw tennis balls toward it. Some bounce away, others pass through the openings. Place a second wall behind the first and the balls that pass through will strike it. Mark the points of impact, and you would expect to see two distinct bands corresponding to the slits. Simple, intuitive, entirely reasonable. But now replace the tennis balls with light. Light behaves not only as a wave, but also as particles known as photons. Fire a single photon toward the double slit, and something extraordinary happens. On the back wall, an interference pattern appears as though the photon passed through both slits simultaneously and interfered with itself. It becomes stranger still when we attempt to observe which slit the photon travels through. The very act of looking causes the interference pattern to vanish. The photon behaves differently, simply because it is being observed. It is as though observation reaches backward in time, altering events that have already occurred. We do not yet fully understand how this can be. Perhaps one day someone will. Finally, consider another cosmic puzzle, the faint young sun paradox. According to the standard model of stellar evolution around 4 billion years ago, the sun produced roughly 30% less energy than it does today. With significantly less warmth reaching Earth, astronomers suggest our planet should have been frozen solid during those early epochs, and yet evidence tells us it was not. Yet some scientists argue that this picture is not what truly unfolded. When we look at climate models of Earth during the Archean eon, from 4,000 to 2,500 million years ago, they suggest a world that was surprisingly warm and humid, not unlike our planet today. There was no permanent ice at the poles. In the oceans, single-celled prokaryotes drifted through the water, releasing oxygen as a byproduct of their existence, oxygen that would later make complex life possible. At first glance, these two ideas seem to clash. If the young sun was faint, how did the Earth remain warm? And yet the evidence points toward a planet that somehow sustained gentle life, friendly conditions throughout this era. One possible answer lies beneath our feet. The Earth's crust was still cooling after the planet first formed, retaining immense internal heat. Gravitational compression also played its part slowly, squeezing the planet and releasing energy. There is strong evidence that a colossal collision with a protoplanet, likely comparable in size to Mars, occurred early in Earth's history. From this cataclysm, the Moon was born. In those early days, the gravitational interaction between the Earth and the Moon was extreme. Tides surged across the planet with extraordinary force, and the Moon became tidally locked in just 100 million years after its formation. This tidal interaction may have generated significant heating, raising surface temperatures, and driving widespread volcanic activity across the globe. These volcanoes poured vast quantities of gas into the atmosphere, creating a powerful greenhouse effect. Carbon dioxide and methane were almost certainly the dominant contributors. At the same time, the Archean sky was remarkably clear. Clouds usually form when sunlight evaporates water, but with much less incoming light from the young sun, cloud formation was limited. The few clouds that did exist reflected very little of the star's radiation back into space. Enormous concentrations of methane may also have produced a thin photochemical haze, tinting the sky and clouds with a soft pink hue. This alien spectacle persisted until near the end of the Archean eon, when rising oxygen levels caused methane to oxidize. As methane declined, the haze vanished, and clouds took on the familiar bright white appearance we recognize today. We often associate strangeness with the distant universe, but some of the deepest mysteries lie much closer to home within and around our own Milky Way galaxy. One of the most profound puzzles in modern physics is the black hole information paradox, born from the uneasy marriage of quantum mechanics and general relativity. Calculations suggest that information about physical systems could vanish forever inside a black hole, allowing many distinct states to collapse into a single outcome. This is deeply troubling because quantum mechanics insists that information can never be destroyed. Imagine burning two different letters written on paper. Reassembling them from ash would be almost impossible, but not completely. Subtle differences in smoke, temperature, and ash distribution would still carry traces of the original information. Black holes, however, appear far more ruthless. They consume matter and energy, and over unimaginably long timescales they release what they have absorbed as Hawking radiation. The problem is that this radiation seems to be identical in all cases. Unlike the smoke and ash from a fire, Hawking radiation appears to carry no imprint of what fell in. If that is true, then black holes truly erase information from the universe. So, the question remains, when a black hole evaporates, is information destroyed, or does it somehow escape? A new generation of physicists believes it does escape. They propose the existence of an invisible boundary hidden within the event horizon known as the quantum extremal surface. This surface seems to encode the information carried away by radiation, evolving over the lifetime of the black hole in precisely the way we would expect if information is preserved. If this idea is correct, then even black holes are not quite the prisons we once imagined. Another cosmic mystery unfolds much closer to home. According to the standard model of cosmology, large galaxies should be surrounded by hundreds, perhaps thousands of smaller dwarf satellite galaxies. Yet around the Milky Way, we have identified only about 30. That is roughly 1% of the number predicted. So, where are the missing dwarf galaxies? One possibility is that larger galaxies captured and absorbed them long ago. Another is that violent cosmic events erased them from view. Or perhaps they are simply too faint for us to detect. Many of these dwarfs are extraordinarily small and dim, containing only a few thousand stars. By comparison, the Milky Way shines with 100 to 400 billion stars, utterly overwhelming the feeble glow of its tiny companions. The mystery deepens further. These ultra-faint dwarf galaxies do not behave as our current models predict. Their motions challenge the traditional Newtonian description of gravity. In theory, satellite galaxies should form independently, and later be captured from many different directions, leading to a scattered distribution. Instead, the 11 brightest dwarf galaxies are arranged in a disk-like structure, all orbiting the Milky Way in the same direction. It is an unexpected order written across the sky, hinting that our understanding of gravity and galaxy formation may still be incomplete. This arrangement is not unlike the way the planets in our own solar system circle the Sun, yet scientists argue that such an orderly structure could only exist if gravity were stronger than Newton ever predicted, and that is precisely where the paradox appears. Researchers propose that dark matter gathered within these tiny galaxies is simply not massive enough to pull in gas and ignite star formation, which would render them invisible to our telescopes. And yet it is dark matter that provides the gravitational glue holding cosmic structures together, and there must be an enormous quantity of it. Astronomers at Cambridge University examined around 7,000 galaxies and concluded that there is roughly 400 times more dark matter than ordinary matter. However, in May 2022, astronomers at the University of Barcelona in Spain reported the possible discovery of 11 galaxies that seem to contain no dark matter at all, even though they exist within regions dominated by dark matter. Inside galaxies filled with dark matter, stars should move far faster than Newtonian gravity allows. So, if the Spanish observations are confirmed, Newton's theory itself would need revision. This would not be unprecedented. Every time the foundations of physics shift, our picture of the universe changes profoundly. We have built the internet, walked on the moon, uncovered the Higgs boson, and sent spacecraft beyond the boundary of interstellar space. It feels as though in just the past 100 years we have achieved more than anyone might once have imagined, and it is tempting to believe there is little room left for further progress. But what if all of this is merely the beginning? What if human advancement is only a collective illusion when measured against cosmic time? The Kardashev scale, a way of ranking civilizations by their technological maturity, stretches our perspective both outward and inward. One interpretation of this scale describes 4 levels of civilization. A Type 1 civilization, also known as a planetary civilization, would be able to capture and use every available energy resource on its home world. A Type 2 civilization, a stellar civilization, would go much further, drawing power from an entire star and effectively commanding a complete planetary system. A Type 3 civilization, a galactic civilization, could exploit the energy of a whole galaxy, shift planets from their orbits, and even feed stars into black holes. Yet even this pales beside the potential of a Type 4 civilization, capable of creating a universe of its own. According to this scale, humanity has not yet reached Type 1 status, though we have moved beyond Type 0. Type 0 corresponds to a specific energy usage, roughly 1 megawatt of power. Today, our average annual energy consumption is about 17.7 terawatts, and a single terawatt alone could illuminate 10 billion light bulbs, rated at 100 watts each at the same time. By this measure, humans score around 0.73 on the Kardashev scale. The question then becomes how quickly we might reach the milestone of a Type 1 civilization. One prominent theoretical physicist has suggested that if our energy use grows by 3% each year, it would take between 100 and 200 years to arrive there. At present, only about 1 billionth of our star's energy reaches Earth, and we exploit merely 1 millionth of that. When we finally attain this level, we would be able to harness all available sunlight, wind, and tidal power. Weather patterns could be shaped at will, earthquakes and volcanoes redirected, and entire cities could float upon the oceans. It sounds almost like possessing superpowers, yet it is modest compared with what a Type 2 civilization could achieve. A stellar civilization would extend far beyond the limits of its planet. At this stage, intelligent beings could control the full energy output of their parent star. There are several theoretical ways to accomplish this. One is the construction of an immense structure known as a Dyson sphere. In a simplified form, a Dyson ring would be made up of countless solar collectors orbiting a star at, for example, around 160 million kilometers. As technology advanced, additional rings could be added, each following its own path. In time, this vast assembly, comparable in size to the orbit of our planet around the Sun, would resemble a shell surrounding the star, blocking much of its light while capturing most of its energy. Creating such a system would be almost as transformative as the invention of electricity itself. Another approach involves star lifting, a process by which material is drawn directly from a star. A highly advanced civilization approaching Type 3 status might know how to siphon stellar matter and feed it into the ergosphere of a rotating black hole. The ergosphere is the region outside a black hole's event horizon where extraordinary physical effects occur. By injecting material into this zone, it is theoretically possible to extract energy at far greater speeds, a mechanism known as the Penrose process. In principle, about 29% of a black hole's energy could be recovered this way. There is a cost, however. As energy is removed, the black hole slows its spin until it eventually comes to rest. Yet this limitation hints at another possibility: the capture of Hawking radiation from evaporating black holes. Such a feat lies far beyond our current abilities, but for a Type 3 civilization, it would scarcely be a challenge at all. A civilization operating on a truly galactic scale would not rely on fundamentally different principles from those that came before it, but it would apply them on an almost unimaginable magnitude. We are no longer talking about individual stars or solar systems, but about entire galaxies as the stage for technology. Vast stretches of space would be populated by Dyson spheres, enclosing billions of stars, while new planetary systems could be engineered deliberately rather than formed by chance. With access to energy on such a colossal scale, their power supply would for all practical purposes be limitless. In that sense, they would approach immortality with the only real danger to their continued existence being rare, violent cosmic events, such as the catastrophic explosion of a nearby supernova. For humanity, reaching this level of sophistication would require at least 100,000 years, and perhaps as long as 1 million years, assuming we manage to survive long enough to become what is known as a Type 3 civilization. This naturally leads to a profound question. Do such civilizations actually exist? And if they do, their technological activity would be so intense that it should be clearly visible across space. Over the last 2 decades, according to NASA, we have identified around 4,000 planets beyond our solar system. In the Milky Way alone, there should be trillions of stars, many of them accompanied by planets. Given those numbers, why have we not detected any clear evidence of advanced life? This puzzle is known as the Fermi paradox. It points out that the universe is both extremely old and extraordinarily vast, so it seems unlikely that life would arise only once here on Earth. And yet, despite decades of searching, we have found nothing definitive. It may simply be that we have not been looking in the right way or with sufficient sensitivity. Our current search for extraterrestrial intelligence is largely limited to detecting narrow bands of radio and television frequencies. The difficulty is that such signals are characteristic of a Type 0 civilization, one like our own. Even then, these signals interact with charged particles and background noise in space, causing much of the information to be lost along the way. A far more efficient method of communication would be to spread a signal across all frequencies, preserving its integrity. However, a hypothetical Type 0 civilization listening on only a single frequency would be unable to reconstruct such a message, and would perceive it as meaningless noise. As a result, even if the Milky Way were filled with messages from Type 2 or Type 3 civilizations, our comparatively primitive radio telescopes would be incapable of hearing them properly. In an effort to address this, a researcher at the National Astronomical Observatory of China proposed a different idea about where these civilizations might be concealed. A professor and her team surveyed a substantial portion of the sky, identifying 21 galaxies in their search. They were specifically looking for unusual radio signatures that could indicate the waste heat or exhaust of alien technology. Among their findings were two particularly strange galaxies, exhibiting enhanced infrared emissions that could not be explained by known natural processes. Astronomers hope this may point to large collections of Dyson spheres, or even entire galaxies harnessed by one or more intelligent civilizations. To confirm such a hypothesis, however, they must first determine the true source of these infrared signals. There is also a more unsettling resolution to the Fermi paradox. It is possible that advanced civilizations have deliberately chosen to remain hidden. The universe is vast, and our failure to detect others does not necessarily mean they are absent. When astronomers search for technologically advanced societies, they typically focus on infrared emissions and other forms of energetic waste. But what if a super-intelligent civilization has developed not only astonishing technologies, but also perfect methods of concealing its presence? If that is the case, then for all this time we may have been searching for the wrong clues while overlooking what truly matters. If our attempts to find evidence of extraterrestrial civilizations continue to fail, another approach would be to study what is missing rather than what is present. One possibility is that a Type 3 civilization, if it existed, would eventually harvest all the available energy within a galaxy, depleting it entirely and leaving behind regions devoid of usable power. There are indeed vast empty areas in space known as great voids, which were once thought to be signatures of intelligent life. That idea has since been rejected, and although scientists remain hopeful, many investigations ultimately reach a dead end. If that is always the outcome, another question emerges. What if we have simply arrived at the wrong moment in cosmic history? According to one computer simulation, intelligent life may have been more common 4 billion years ago than it is today. This might sound surprising, but if primitive life appeared on Earth around 3.5 billion years ago, there is no obvious reason why intelligent life could not have arisen elsewhere in the universe at roughly the same time. This raises a further dilemma. Should we even be trying so hard to satisfy our natural curiosity, given the potential risk of bringing about our own extinction as a species? We all descend from a single ancestor, and yet we struggle to restrain our hostility toward one another. Is it reasonable to expect that a hyper-advanced civilization would value our lives more than we do ourselves? We worry about exhausting the resources of our planet. A Type 2 civilization would fear the eventual death of its star. A Type 3 civilization would be preoccupied with how to escape the ultimate demise of the universe itself. But when we extend the Kardashev scale further to a Type 4 or even a Type 5 civilization, even these concerns would fade. Such beings could, at least in theory, create an entirely new universe, and according to one physicist, this possibility lies at the very edge of what the laws of physics might allow. The amount of energy required to bring a baby into existence is immense, yet to recreate a universe inside a laboratory would demand temperatures of around 1,000 trillion degrees, a value that still lies well below the ultimate limits, imagined for a civilization of sufficient technological maturity. Although a Type 4 civilization remains almost impossibly rare, achieving it would effectively mean becoming the architects of everything we could ever observe, think about, or even dream of. When you consider the extraordinary speed of our own technological development and the fact that even today we are already capable of designing tiny spacecraft propelled by lasers, it becomes conceivable that our world may have been visited, in the distant past, with the probability of detecting such, a presence being almost zero. Even now, it is entirely possible that we are being watched by a far more advanced civilization, one that is simply waiting for us to reach a certain level of understanding before initiating contact. Or perhaps contact has already been decided upon, but the journey itself could take hundreds of thousands of years for travelers crossing from a galaxy on the far side of the universe. Yet even if we never discover anyone else out there, that outcome does not necessarily carry a bleak message. Of course, there might be a sense of loneliness, even abandonment, but it would also mean that we have been given a unique opportunity to lay the foundations for the future stages of human evolution. One day, those hyper-intelligent beings, perhaps not so different from us in appearance, might look back and regard us as pioneers, explorers, feeling our way through the darkness of a vast cosmos, much as a child slowly learns to understand the world around them. It may be that our belief in other civilizations is simply a creation of our imagination, or perhaps they do exist but they are not some distant species at all. Perhaps they are us, far in the future, transformed into something profoundly superhuman. You may have encountered the idea often referred to as the great cosmic question of absence, which in its simplest form asks this: if intelligent life is common throughout the universe, then why do we see no sign of it? It is easy to assume that the physicist associated with this question devoted a lifetime to the search for alien civilizations, but that assumption is mistaken. He was primarily concerned with nuclear physics and was responsible for building the world's first prototype nuclear reactor, and he wrote very little about life beyond Earth. The question itself arose casually during a lunchtime conversation at a research facility, prompted by a cartoon depicting aliens emerging from a flying saucer while carrying rubbish bins taken from New York City. At that moment, he asked a deceptively simple question: where is everybody? Everyone present understood that he was pointing to the absence of any solid evidence that extraterrestrials had ever visited our blue planet. The discussion then shifted toward the practicality of traveling between stars, and he suggested that such journeys might not be feasible, might not be worth the immense effort, or that technological civilizations might not survive long enough to develop interstellar travel at all. It is important to remember that this conversation took place in the year 1950, at a time when rockets had not yet even reached Earth's orbit. The so-called paradox that bears his name is therefore something of a misunderstanding. He was not questioning whether alien civilizations could exist, only whether they could realistically travel between the stars. So what then is this paradox, if it did not originate with him? In 1975, an astronomer published an article arguing that if extraterrestrial civilizations existed, they would already be here, and since they are not, they must not exist at all. The claim was that any sufficiently advanced civilization would inevitably spread throughout the Milky Way. If such beings were present anywhere in our galaxy, they should have reached our region by now. Since we observe no evidence of them, the conclusion drawn was that humanity represents the only intelligent life in the galaxy, making the search for others a probable waste of time and resources. A few years later, another physicist expanded on this idea and posed an even larger question: where would a civilization find the resources necessary to colonize 1 billion stars? He proposed a striking solution. A civilization might construct an artificially intelligent machine comparable to humans in capability that could replicate itself. If one such machine were sent to a neighboring star system and instructed to build copies of itself using materials found there, those copies could then be dispatched onward to other nearby stars. Over time, the entire galaxy could become filled with these self-replicating machines. Since we see no evidence of such devices, he argued, it follows that we must be the only intelligent civilization in the galaxy. In truth, we have no real idea how many advanced civilizations might exist that are capable of accomplishing feats like this. However, another scientist introduced an equation designed to provide a rough estimate of how many technological civilizations might inhabit our galaxy, offering at least a framework for thinking about this profound and humbling question. In our galaxy, there may be signals that in principle we could detect, and although civilizations might exist in the thousands, many explanations for the Fermi paradox have been proposed over the years. One possible answer to that paradox may also be the most unsettling of all, an idea known as the dark forest theory, and it is deeply disturbing once you follow its logic. Imagine the universe as an immense shadowed forest. We, as humans, along with other advanced civilizations, are like hunters moving silently among the trees. A hunter does not light a torch because drawing attention could be fatal. What seems harmless at first glance might instead summon the jaws of a hungry predator, or worse, reveal your position to a rival hunter waiting in the darkness. We do not yet possess interstellar travel, but interstellar communication is already within our reach. With technologies that exist today, lasers could transmit signals across the galaxy. Of course, those signals would be delayed by the finite speed of light, but even so, we have done far more than quietly listen. In truth, we have done almost everything except remain silent. From deliberate attempts to send messages and spacecraft into space to the unintentional leakage of radio and television signals escaping Earth, we have announced ourselves. The Voyager probes are already leaving the solar system, and if an intelligent civilization exists out there, they could one day intercept them. Those probes carry a portrait of humanity with them, and that could be a blessing or it could be a profound mistake. In the language of the dark forest, we have not merely lit a torch, we have set it blazing. The question that follows is deeply uncomfortable. Who or what might notice our signal and decide to investigate? That thought alone should make us uneasy. There is an old observation that only two possibilities exist. Either we are alone in the universe, or we are not, and both possibilities are equally terrifying. We must accept that it would be impossible to know the intentions of a newly discovered civilization. It is conceivable that another society might study us, observe our destructive tendencies, and decide it is safer to keep its distance. We are quite capable of destroying ourselves without any external help. On the other hand, we might imagine a more optimistic outcome, where a far more advanced civilization intervenes, helping us reach the stars and sharing its technology. Perhaps the realization that we are not alone could even bring peace to Earth, but realism demands a harder question. Why would another civilization choose to help us? From their perspective, they might be terrified of what we could become if we were allowed to grow and spread. From a colder viewpoint, it might seem rational for a civilization to strike first and ask questions later, simply to avoid the risk of being destroyed by a rival that grows too powerful. Popular stories have explored this idea many times, where first contact ends in annihilation, and the truth is that no one can know who would destroy whom in such an encounter. If a civilization has mastered interstellar travel, its weapons technology would almost certainly be far beyond anything we possess on Earth. This is the essence of the dark forest idea. It suggests that other civilizations may have chosen silence as a survival strategy, hiding in the cosmic undergrowth for fear of being wiped out. The most unsettling part is that there is nothing we can do to undo our noise. We have already spoken too loudly. It is possible that many extraterrestrial civilizations already know we exist, and the reason we know nothing of them is simply because they have chosen not to transmit signals as we have. A civilization that has discovered Earth might not yet see us as a threat since we have not achieved interstellar travel, but they could be waiting to see whether we remain peaceful or whether our world renders itself uninhabitable through our own actions. Avoiding accidental radio leakage as we experience it would be extremely difficult unless a civilization were far more advanced than we are, perhaps using forms of communication we cannot detect or even comprehend. That leads to another possibility altogether. Perhaps there really is no one out there. That idea is difficult to accept, especially when we consider that there may be as many as 40 billion Earth-sized planets in habitable zones. Yet even if the universe is filled with potentially welcoming worlds, there is no guarantee they remain stable long enough for life to evolve. Research suggests that wet, rocky planets like Earth are highly unstable when they first form. If life is to arise and flourish on a terrestrial planet, there may be only a narrow window of a few 100 million years for conditions to settle. Consider our own planet's history, from a molten sphere battered by asteroids to a frozen world of ice and then back again. The odds of life succeeding under such chaotic beginnings are extremely small. Life itself may not be rare, but stable, habitable environments during the first billion years may be. And yet, against those odds, here we are. Our own discoveries show us that the universe is a dangerous place. A supernova, a gamma ray burst, a powerful solar flare, or a large asteroid impact is enough to erase life from a planet. Some of these events have already occurred on Earth. It is unsettling to contemplate that we might be the only intelligent life in the Milky Way, or perhaps even in the entire universe. Or it may be that after billions of years, other civilizations rose, flourished, and vanished, and that we are simply the last ones left standing alone in the cosmic dark. When we talk about the Fermi paradox, the truth is that there may not be a paradox at all. We cannot honestly say whether alien civilizations exist or not, because at a fundamental level, we still do not know if travel between star systems is even possible. There was a surge of public excitement when the Central Intelligence Agency declassified thousands of documents related to unidentified flying objects. But among those roughly 3 million files, there was still no conclusive evidence that the objects detected by aircraft instruments were anything other than unexplained phenomena. It is conceivable that extraterrestrials are already present and simply remain unnoticed. Yet regardless of whether our galaxy has ever been visited, experts who study unidentified aerial phenomena argue that humanity is closer than ever to discovering evidence of alien life. With the vast array of telescopes now scanning the cosmos, it feels inevitable that something will eventually reveal itself. So the question naturally arises, do you think we will find signs of life beyond Earth in the near future, and should we continue the search? While that question lingers, astrophysicists are also grappling with another profound mystery, trying to understand what is capable of destroying entire galaxies in the most extreme regions of the universe. Scientists at the International Centre for Radio Astronomy Research in Australia examined more than 1,000 galaxies and found that their gas and dust are being stripped away. Without this raw material, galaxies can no longer form new stars, and over time, the existing stars slowly fade. This leads us to ask what could possibly be devouring galaxies. Is there some unknown galactic monster at work, or are there cosmic processes we have yet to fully grasp? One proposal suggests that the ever-accelerating expansion of the universe may be responsible. Speed, it turns out, may be just as dangerous in space as it is on a highway. When galaxies move too rapidly within their clusters, turbulent storms can arise powerful enough to force gas out of them at remarkable rates. But this is not the only possibility. Black holes are believed to sit at the centers of most galaxies, and as matter spirals inward, intense radiation is released. From this process emerge colossal streams of particles known as cosmic jets, which can blast material out of a galaxy altogether. Another idea is more subtle and almost tragic. Some galaxies may be digging their own graves, burning through their stars far more quickly than their neighbors, and leaving themselves no time to replenish their gas reserves. This slow decline, which astronomers refer to as strangulation, eventually leads to their extinction. Whatever the true cause of this widespread destruction may be, scientists continue to struggle to explain the existence of certain galaxies that simply do not behave as expected. Among the many puzzles that still confound us are worlds known as red-hot Jupiters. These are enormous gas planets similar in nature to Jupiter, yet they orbit astonishingly close to their parent stars. Their very existence challenges our understanding of planetary formation. To explain them, scientists have proposed three main hypotheses. One suggests that the magnetic field of the host star may act as a protective shield for a gas giant. Another proposes that the defining boundary for such a planet lies within its dust disk, where a gap forms between the inner edge of the disk and the star, weakening the star's gravitational pull. A third idea suggests that as a planet migrates inward, its approach halts when the elongated orbit of a hot Jupiter becomes circular. As researchers search for evidence to support these ideas, these giant worlds continue to surprise us. Consider WASP 121b, located in the constellation Puppis, about 850 light-years from Earth. This planet has a radius 1.74 times that of Jupiter and a mass 1.157 times greater. It orbits so close to its star that it completes a full revolution in just 30 hours, an astonishing 68 times faster than Mercury orbits the Sunday. On the cooler side of this planet, clouds form from particles of molten iron, magnesium, chromium, vanadium, aluminum, and titanium. In that environment, aluminum combines with oxygen, and together with mixtures of chromium, iron, titanium, or vanadium droplets, can form that are essentially rubies or sapphires, potentially falling as rain. Yet no form of alien life could ever exploit such gemstones, because the planet's proximity to its star raises temperatures to around 2,700 degrees Celsius, making protein-based life impossible. Although most objects in the universe end quietly fading away over immense timescales, some meet a far more dramatic fate. In 1967, the Vela satellite, originally designed to monitor covert Soviet nuclear tests, detected an intense flash of gamma rays coming from beyond the solar system. Gamma rays are among the most energetic forms of electromagnetic radiation known, and today astronomers observe roughly one gamma ray burst each day in distant galaxies, each one a reminder of just how violent and extraordinary the universe can be. These flashes in space arise from some of the most intense and luminous explosions the universe can produce. Their lifetimes can be astonishingly brief, lasting as little as 10 milliseconds, or they can endure for several hours. When such an event unfolds, the energy released can rival the total output of our Sun over 10 billion years. Astronomers have identified stars that in their final moments reduce everything around them to dust. Long-lasting gamma-ray bursts are associated with hypernovae, the catastrophic deaths of stars exceeding 30 solar masses. In some cases, these explosions are 100 times more powerful than an ordinary supernova. What remains after such violence are enormous, rapidly spinning black holes. Short-lived gamma-ray bursts are thought to originate from neutron stars. As ripples pass through space itself, a neutron star may collide with another neutron star, or it may be consumed by a black hole. The true nature of these events is still not completely understood. Recent observations reveal something even more curious. After a gamma-ray burst occurs, all the photons initially travel in the same direction, and then at a certain point in space they abruptly and inexplicably change course. It is also remarkable that the energy of gamma-ray bursts is concentrated into a very narrow beam, which is why our satellites detect so few of them. Astronomers estimate that there may in fact be around 500 gamma-ray bursts taking place every day. Scientists believe that the Laser Interferometer Gravitational Wave Observatory, an instrument exquisitely sensitive to gravitational waves, will be able to record many more of these events. One can only hope that gamma-ray bursts never occur anywhere near the Milky Way. One such burst was observed close to our galaxy about 450 million years ago, and it is thought to have triggered an ice age on Earth that ended with the Ordovician extinction, one of the 5 largest mass extinctions in our planet's history. A new burst occurring near Earth today would likely destroy the ozone layer, and as a consequence all life would be exposed to lethal ultraviolet radiation and would cease to exist. Fortunately, because there are no neutron stars nearby nor suitable candidates for supernovae or hypernovae in the vicinity of the Milky Way, scientists are confident that the probability of such an event is close to zero. Undoubtedly, other dangers to our solar system and our planet will be discovered in the future, but for now there seems to be little to fear aside from the occasional asteroid that passes our planet unexpectedly. Most galaxies are arranged along filaments of gas and dust stretching between stars, forming a kind of cosmic skeleton that appears to hold everything together. Just seconds after the Big Bang, dark matter and dark energy spread throughout space, creating a vast web. Dark matter seems to be responsible for the large-scale structure of the universe as we observe it today. But this raises an obvious question. What exactly is this substance? Dark matter is believed to be a non-luminous form of material that accounts for around 27% of the universe. It may exist in many possible forms, including weakly interacting particles or rapidly moving high-energy particles. Dark energy, by contrast, is an unknown form of energy that appears to make up roughly 68% of the universe. Researchers uncovered evidence for dark energy by studying supernovae, which revealed that the expansion of the universe is not constant, but is instead accelerating. Put simply, dark matter acts like a kind of glue or cement, binding the universe and everything within it together, while dark energy is the mysterious force pulling on the universe in all directions and driving its expansion ever faster. So, why does this matter? Consider the galaxy known as NGC 1052 DF2 in the constellation Cetus, located 62 million light-years from Earth. At first glance, the image seems unremarkable, aside from the fact that this galaxy contains far fewer stars than the Milky Way. Yet that is not what truly captured the attention of scientists. This galaxy, along with its neighbour NGC 1052 DF4, appears to be missing dark matter entirely. The largest map of the universe's dark matter, created by astronomers at an observatory in Chile, highlights this extraordinary phenomenon. So why is dark matter absent from these galaxies in Cetus? And how do they manage to survive without flying apart? One possibility is that larger neighbouring galaxies stripped gas from DF2 and DF4, gradually tearing their smaller companions apart. More recent studies suggest that around 8 billion years ago, 2 dwarf galaxies collided. This cosmic catastrophe redistributed gas and led to the formation of many new dwarf galaxies. Eventually, 2 of these newborn galaxies failed to acquire dark matter, and they have been forced to endure without a skeletal framework. Yet this is not the only mystery troubling astronomers. More than 400 exoplanets discovered so far should not have survived at all. We tend to think of gravity as a force acting between objects with mass. Its effect is easy to grasp when you step onto a scale and read your weight, a direct measure of Earth's gravity acting on your mass. But when it comes to gravity in the cosmos, we can picture the sun's gravity holding the planets in their paths, and we are all familiar with the immense gravitational influence close to a black hole. What we casually call the force of gravity feels intuitive and almost obvious, something straightforward and easily grasped. Yet in the modern era, our understanding has shifted. We now know that gravity, when described merely as a force, represents only a fragment of a far richer and deeper reality, revealed to us through the general theory of relativity. Before we reach that point, however, it is worth returning to some fundamental physics. Everyone knows of Isaac Newton, a towering figure of science in his era, often portrayed as almost godlike in his influence. The well-known tale of an apple striking his head is a myth, of course. What truly happened is that Newton observed an apple falling from a tree while he was deep in thought. In that moment, he asked a deceptively simple question. Why did the apple fall directly downward rather than drifting sideways or moving in some other direction? From this reflection, he proposed that there exists a gravitational interaction between any two bodies, drawing them toward one another with a strength proportional to their masses and inversely proportional to the square of the distance, separating them. According to this view, objects follow the most efficient path, the one that minimizes energy, which in ordinary circumstances is a straight line. In essence, Newton concluded that an apple falls because a gravitational force accelerates it toward the Earth. Yet it seems Newton himself sensed an incompleteness in his explanation, as historical accounts suggest he was never entirely content with it. Initially, he even imagined gravity as a kind of push rather than a pull. Unbeknownst to him, that intuition was not entirely misguided. Still, his model of gravity was embraced as absolute truth, the idea that an invisible attractive force was an inherent property of mass. This framework endured for nearly 400 years, both illuminating nature and concealing a deeper truth until the arrival of another extraordinary mind. In 1905, Albert Einstein, working quietly as a Swiss patent clerk, introduced ideas that would culminate in the general theory of relativity. His challenge to Newton's picture of gravity was met largely with skepticism or dismissal, as it appeared far too radical to be credible. The central insight of general relativity is that all objects within a gravitational field fall at the same rate. Interestingly, this realization did not originate with Einstein. It was Galileo who first recognized that in the absence of air, objects released together will fall identically regardless of their mass. This principle was dramatically demonstrated during the Apollo 15 mission, when astronaut David Scott performed an experiment on the Moon. Holding a hammer and a feather, he released them simultaneously, and both descended gently and struck the lunar surface at the same moment. The same outcome would occur for any objects independent of their composition or weight. This observation is known as the equivalence principle. So why do these two objects fall together and arrive at the ground at the same time? The answer, according to Einstein, is startling. They are not truly falling at all. They are effectively at rest with no force acting upon them. In Einstein's view, gravity is not a force exchange between masses. Instead, it arises from the distortion of space and time caused by mass itself. Without any external influence, objects simply move along straight paths. Einstein proposed that smaller bodies are not pulled by larger ones, but rather are pushed by the geometry of space above them. In this framework, there is no gravitational force in the traditional sense. Matter, according to relativity, bends not only space but time as well, forming what we call space-time. Every object in the universe deforms this space-time continuum. Space-time consists of the three familiar dimensions of length, width, and height unified with the fourth dimension, time. The greater the mass of an object, the more pronounced this curvature becomes. In this picture, apples fall from trees and planets, circle stars, because they are following curved paths within space-time itself, and those curves are what we perceive as gravity. A helpful way to imagine this is to picture the Earth embedded in a grid representing space-time. The Earth's mass bends this grid, creating a depression often described as a gravity well. Everything nearby, including you, me, and even the Moon, moves within this curved landscape. The Moon, with its own mass, also distorts space-time, but the curvature between Earth and Moon is such that the Moon does not plunge toward us. Instead, much like an endlessly falling apple, it continues along its orbit. The Sun creates an even deeper gravity well, one vast enough to keep the entire solar system bound together, preventing the planets from drifting away into the void. We can see practical evidence of these gravity wells in the way spacecraft are navigated. By carefully guiding probes near planets, engineers exploit the curvature of space-time around those worlds. This technique, often called a gravitational slingshot, redirects spacecraft and increases their speed. The closer a spacecraft passes to a planet, and thus the deeper it dips into that planet's gravity well, the greater the boost it receives as it is flung onward through space. An object begins to move, and at its heart the explanation is simple yet profound. Objects throughout the universe are drawn toward one another because space-time itself is bent and curved. The nearer an object is to a mass, the more rapidly it accelerates. But what then of this thing we call a gravitational field that we mentioned earlier? Is it truly a force at all? A gravitational field is better understood as the field that exists in space around every object that has mass. The Moon possesses a weaker gravitational field than a planet because it has less mass. The Earth, by contrast, generates a far stronger gravitational field than the Moon precisely because it is more massive. And yet, throughout the cosmos, a gravitational field exists almost everywhere, with everything suspended in the vastness above our heads. It is tempting to imagine that no gravity is at work in orbit around our blue planet, but even the International Space Station is firmly within Earth's gravitational grip. What is surprising is that the effective gravity in orbit is almost the same as it is at the surface. In fact, it is about 90% as strong in orbit as it is on the ground. If you weighed 100 kilograms on Earth and could somehow climb a ladder reaching all the way up to the space station, you would still weigh about 90 kilograms once you arrived. So why, if gravity is present in space, do astronauts appear to float as though there is none at all? The reason is that everything, including the International Space Station itself, is falling together at the same time through the vacuum of space. This state in which people and objects seem weightless is known as microgravity. If all objects fall in exactly the same way, regardless of their mass, then a freely drifting astronaut far from any gravitational source and an astronaut falling within the gravitational field of a massive body would experience precisely the same sensation. In reality, the space station, its satellites, and everything up there are constantly falling toward Earth. While the International Space Station is falling, it is also moving sideways at extraordinary speed, about 2,800 kilometers per hour, balancing the pull of Earth's gravity. There are ways to demonstrate that Einstein was right when he said that objects with mass warp the fabric of the universe we call space-time. The gravitational acceleration at Earth's surface is 9.81 meters per second squared. The reason gravity pulls you and everything else toward the ground has nothing to do with the planet's core. All objects with mass bend and curve space-time, and that curvature itself is gravity. If you could somehow travel to the very center of the planet, there would be no gravity at all. At the center, you would be removed from the curvature of space-time, and you would float weightless near the core. But as you journeyed back toward the surface, you would begin to feel the curvature caused by Earth's mass, and gravity would steadily grow stronger. One day, perhaps a probe will make that journey to the center and confirm it directly. There is, however, another powerful way to show that gravity warps space-time, and it is known as gravitational lensing. This occurs when a massive celestial object curves space-time so strongly that light passing nearby appears visibly bent, much like light passing through a camera lens. Gravitational lensing can produce rings and arcs of light when massive objects such as galaxies distort the space around them. Remarkably, this effect has allowed us to discover distant galaxies and cosmic structures that would otherwise remain invisible. Einstein's cross is a striking example. It reveals a quasar positioned directly behind the center of a galaxy, appearing as 4 distinct images in the foreground due to the intense gravitational lensing caused by the galaxy in between. It might seem that Einstein solved gravity completely, and indeed the evidence supporting general relativity is overwhelming. Yet there is a profound problem. In its current form, the theory does not align with quantum mechanics. Quantum gravity is the field of theoretical physics that seeks to describe gravity using the principles of quantum mechanics, but so far, no single theory has been universally accepted or experimentally confirmed. Beyond that, scientists know that somewhere within a black hole, Einstein's theory breaks down and can no longer describe reality. To test these ideas, researchers used 3 enormous telescopes in Hawaii to observe a blue star known as SO2 as it made its closest approach to the black hole Sagittarius A star at the center of the Milky Way during its 16-year orbit. If Einstein was correct, the black hole would warp space-time and stretch the wavelength of the star's light. As the intense gravity drained energy from the light, its color would shift from blue toward red, exactly as Einstein had predicted. As the star began to glow red, had it appeared in any other hue, it would have pointed toward an entirely different understanding of gravity. At this very moment, scientists are searching for regions where the curvature of space-time becomes so extreme that general relativity itself can no longer describe reality. Many believe that within the next 10 years, Einstein's great theory will be driven to its breaking point, and that another brilliant mind will emerge to reveal where it falls short. One can only hope that such a revelation does not require another 300 years of waiting. In 1994, an image from the Hubble Space Telescope seemed to reveal something extraordinary. It appeared to show a magnificent city with pale towers suspended in the darkness of space. Some called it heaven, others the celestial city. Those convinced of alien civilizations were thrilled, even suggesting that this structure marked the very center of the universe. Yet careful analysis told a different story. Astronomers concluded that the image was a fabrication. What Hubble had actually captured was the galaxy NGC 3079, with a portion of the image cut out and digitally altered to create the illusion of a heavenly realm. Although nothing mysterious truly existed in the picture, it ignited widespread fascination with the architecture of the cosmos. This naturally leads to a profound question. Does the universe have a center? And if so, how could we possibly identify it? Since ancient times, the star-filled sky has captivated human imagination. People gazed upward, wondering whether this vast cosmic canvas possessed a central point. Early civilizations explained it through familiar earthly symbols. The Egyptians imagined the sky as a lotus flower, its heart representing the center of the universe where the gods resided. Later, the Greek philosopher Aristotle concluded that the planets, and even the sun, revolved around Earth itself. Then in the 16th century, Nicolaus Copernicus proposed that Earth circles the sun, which was then believed to occupy the universe's central position. By the 20th century, increasingly powerful telescopes transformed our understanding. At the dawn of that century, the American astronomer Harlow Shapley mapped the Milky Way and showed that the sun is merely one among 100 billion stars tucked away in a remote spiral arm of our galaxy. In 1929, Edwin Hubble demonstrated that the universe contains countless galaxies and that our own is far from unique. Today, our planet's cosmic address stretches across many layers: the solar system, the Orion Arm, the Milky Way galaxy, the local group, the Virgo cluster, the Laniakea supercluster, and the universe itself. This alone reveals just how intricate and unimaginably diverse the cosmos truly is. Everything we observe in the universe appears to spin from tiny asteroids to majestic galaxies. This raises another question. Does the universe itself rotate? If it did, we might be able to identify a center. Any spinning object has a fixed point. Earth rotates around an axis, connecting the north and south poles. A basketball spinning on a player's finger rotates around the point of contact. Yet all evidence suggests that the universe lacks such a feature. Unlike stars, planets, and galaxies, it does not rotate, and without rotation, there is no conventional way to define a center. Perhaps mass could offer an answer. If something has an edge, it must have a beginning, and its center would be the point where mass balances evenly in all directions. However, according to the standard model of cosmology, the universe is isotropic. It looks the same everywhere. While galaxies cluster unevenly in certain regions, when viewed on sufficiently large scales, millions of kilometers across matter is distributed evenly. The cosmos resembles a vast cellular sponge, unimaginably enormous in scale. Whether observed from Earth or from the most distant exoplanet ever discovered, the overall pattern remains essentially unchanged. In such a homogeneous space, identifying a center of mass becomes impossible. Still, another aspect of cosmology offers a clue: the expansion of the universe. In 1929, Edwin Hubble measured the velocities of galaxies at various distances from Earth and found something remarkable. Galaxies are receding from us in every direction, and the farther away they are, the faster they move. This suggests that they all began expanding from the same origin. In everyday experience, finding the point from which something expands is straightforward. Secure a rubber sheet to the ground and ask friends to pull it outward from all sides. The fixed point marks the center of expansion. It is tempting to think the same logic applies to the universe. Since we observe galaxies moving away from Earth, perhaps our planet occupies a special central position. Yet the universe does not behave like a stretched sheet. Observations show that galaxies appear to be flying apart no matter where you stand. From any point in space, the same pattern of expansion is seen. Earth is not the center, because in a very real sense, every point is. The farther a galaxy lies from an observer, the faster it appears to be moving away. This relationship is captured in Edwin Hubble calculation known as the Hubble constant. According to this idea, galaxies recede from one another at a rate of 70.4 kilometers per second per megaparsec, which corresponds to 3.26 million light-years. At a distance of 1 billion light-years, the expansion of the universe carries galaxies away from us at 22000 kilometers per second, which is about 7 of the speed of light. Yet at 100 million light-years, that recession speed drops to just 2,200 kilometers per second. From this perspective, observers located in different regions of the universe would measure galaxies moving away at different rates depending on where they are. As a consequence, there is no meaningful way to identify a central point of the universe using this method. But could such a center be inferred from the moment of the Big Bang itself? We believe the universe came into existence around 14 billion years ago in the Big Bang, a profound cosmological expansion. In everyday experience, when an explosion occurs, material flies outward from a definite point, and sometimes that point can be reconstructed even by eye. If you photograph fireworks and trace the paths of light across the sky, it is relatively straightforward to determine where the explosion occurred. It is tempting to imagine applying the same reasoning to the Big Bang. Cosmologists argue that this is not possible not merely because of the immense scale involved, but because the Big Bang took place at a time when space and time themselves did not yet exist. The Big Bang happened everywhere in the universe simultaneously. Only afterward did matter begin to disperse throughout space in a random fashion. We know this through the presence of relic radiation that emerged shortly after the Big Bang, known as cosmic microwave radiation. This radiation fills space in every direction with an approximate temperature of 2.7 Kelvin. In some regions, such as cosmic voids, the temperature of this relic radiation is a fraction of a degree lower, yet no large-scale deviations from the average temperature have ever been observed. If the Big Bang had possessed an epicenter, regions closer to it would be significantly hotter than those farther away. To visualize expansion, scientists often compare the universe after the Big Bang to a two-dimensional balloon with dots drawn on its surface to represent galaxies. As the balloon is inflated, it expands equally in all directions and has no special center on its surface. The dots simply move farther apart from one another. The difficulty with this analogy is the assumption that the universe must have an edge. But what if the universe is infinite? Increasingly, observations suggest this may be the case. If so, we may never determine the true size of the universe, and therefore never identify a center. As expansion accelerates relative to any observer, it must eventually exceed the speed of light. At that point, an event horizon forms around us beyond which we can no longer observe. Could the electric charge of the universe offer a clue? Modern physics indicates that electric charge is distributed homogeneously on large scales. Vast regions of space contain equal numbers of positive and negative charges, resulting in a total electric charge of 0 for the universe as a whole. This means there is no special point to be detected through electric effects either. Everything we observe so far suggests that the universe has no center, and it does not rotate. However, an international team of astronomers has proposed that a center might be inferred through a phenomenon known as dark flow. This hypothesis emerged from studies of galaxy clusters using data gathered by the Wilkinson Microwave Anisotropy Probe. They found that around 1400 galaxies located between the Sales and Centaurus constellations behave in an unusual way. Unlike others that move in more random patterns, these cosmic structures appear to drift in the same direction. A mysterious motion seems to sweep across the entire observable universe, and perhaps even beyond its edge, a vast dark flow moving at a staggering speed of no less than 600 kilometers per second. Cosmologists suggest that this motion gradually draws in ever larger collections of galaxies, pulling clusters toward a single region of attraction. Some have speculated that this destination could be the very center of the universe itself. Scientists have even proposed that such a point might be a black hole, one so immense that it would have no equivalent anywhere in the known cosmos. If that were the case, it raises a profound possibility. Perhaps this colossal black hole is slowly gathering the ingredients for a new Big Bang. For such an event to occur, it would need to draw in and compress all matter and energy in the universe into a single, indivisible point of singularity. An even more intriguing idea follows from this. Passing through the core of such a black hole, our universe might drift directly into a parallel reality altogether. When we sleep, the boundary between dreams and waking life can feel surprisingly thin, and it becomes difficult to say where reality truly lies. So, how do we decide what is real and what is not? In science, something is considered real if its properties exist before we choose to measure them. An apple, for example, can be green even when no one is there to look at it. Yet the quantum world appears to obey very different rules. Recently, 3 scientists were awarded a Nobel Prize for demonstrating that our universe is not locally real. And if our world is not real in that classical sense, then what exactly is this place we inhabit? Imagine 2 people, Anna and Luke, positioned on opposite sides of our solar system. From its center, 2 coins are launched, each one traveling toward a different observer. As the coins move through space, they spin, and according to quantum mechanics, it is impossible to predict which side will face up when they arrive. The outcomes are entirely random. But when Anna observes her coin and finds heads, she instantly knows that Luke's coin must have landed on tails. The probability of correctly predicting such outcomes even 200 times in a row is 1 inch, 10 to the 60, a number greater than the total count of atoms in the solar system. Despite being separated by billions of kilometers, quantum mechanics allows Anna to continue predicting Luke's results based solely on her own measurements, as though the coins shared a strange, invisible connection. This thought experiment is known as the Einstein-Podolsky-Rosen paradox. It feels impossible, and yet it reflects the way the universe truly behaves. How can anything operate faster than light? What is the smallest unit, the pixel of our reality? And how does the universe transition from orderly predictability to fundamental randomness? Before the rise of quantum mechanics, scientists believed the universe was deterministic. They assumed that if enough properties of a physical system were known, its past and future could be calculated with complete certainty. That view changed with the discovery of quantum entanglement, a phenomenon in which two particles remain connected no matter how far apart they are. At first glance, this may not seem remarkable, but consider the implications if those particles were separated by the entire width of the universe. Even within quantum theory, this appears deeply unsettling. We generally accept that nothing can travel faster than light, that there is a universal speed limit governing all signals and influences. Yet, if an entangled pair of particles is created and sent in opposite directions, increasing the distance between them, then the moment one particle is measured, the state of the other becomes instantly defined. You can picture this as two boxes, each containing either a white stone or a black stone. Whenever and wherever someone opens one box, they immediately know what lies in the other. Experiments have demonstrated this effect across distances of hundreds of kilometers over time, intervals shorter than 100 nanoseconds. 1 nanosecond is equal to 1/1000th of a second. If the particles are somehow exchanging information, then that exchange must occur at speeds thousands of times greater than the speed of light. But the story goes further. Just as we step on scales to measure our weight, physicists measure particles to uncover their properties. But what if those properties only come into existence at the moment they are measured? If that is true, then our universe cannot be both local and real. At least one and possibly both of those assumptions must be incorrect. Defining reality turns out to be remarkably difficult. We cannot see tiny particles, yet we know they exist. We cannot touch the air, yet it is undeniably there. In physics, something is considered real if it possesses definite properties, whether or not we are observing it. In that sense, a tree falling in a forest produces a sound even if no one is present to hear it. Locality, on the other hand, means that objects can only be influenced by their immediate surroundings, and that any such influence cannot propagate faster than the speed of light. It matters deeply that the world we inhabit is real, because as Isaac Newton once imagined, if you knew the positions and velocities of every constituent of the universe, and you understood the forces acting upon them, then the laws of physics would allow you to calculate the state of the world at any moment in the future. Yet when we descend into the quantum realm, that certainty dissolves. At this scale, nature often reveals an indeterminate character. Quite simply, events can appear random or beyond precise prediction. Take a simple experiment. Place a number of radioactive atoms into a container and observe them over time. On average, physics can tell you how many atoms are likely to remain and how many will decay. But you can never know exactly which individual atoms will survive and which will not. Or imagine firing particles through a very narrow double slit. You can accurately predict the interference pattern that will emerge on the screen behind the slits, yet you will never know precisely where each individual particle will land, even if they are released one at a time. Certain aspects of quantum physics seem utterly random, but the question remains, are they truly random, or is there something missing from our understanding? Albert Einstein was convinced that quantum entanglement did not violate local realism. He believed instead that quantum theory was incomplete, that there must exist hidden variables linking entangled particles, variables we simply had not yet discovered. Decades later, three scientists, John Clauser, Alain Aspect, and Anton Zeilinger, were awarded a Nobel Prize for demonstrating that these hidden variables do not exist. Their experiments led to a remarkable conclusion. An entangled particle does not possess definite properties until someone measures it. Those properties cannot be known in advance nor inferred by any hidden mechanism. And so if the universe is not fully real in the classical sense, then what exactly is it that we are seeing and experiencing? A group of physicists in Los Angeles have proposed a strikingly different theory of reality, one rooted in periodic patterns and crystals. Crystals, as we know, can take many shapes, but they can also exist in different numbers of dimensions. A crystal in a higher dimension can be projected into a lower dimension, producing a complex pattern known as a quasi-crystal. These physicists began with a specific 8-dimensional crystal and projected it into 4 dimensions at a particular angle. From that projection, they derived a 3-dimensional quasi-crystal, which they believe forms the underlying structure of all reality. The most fundamental building block of this 3-dimensional quasi-crystal is a tetrahedron, a 3-dimensional triangle with all sides of equal length. That length is proposed to be the smallest possible unit of distance in existence, known as the Planck length, which is 10 to the minus 20 times the size of a proton. If an atom were expanded to the size of the Earth, a Planck length would be roughly the size of a proton, and here the idea becomes unsettling. According to this theory, just as a digital display is composed of tiny pixels, a tetrahedron acts as a 3-dimensional pixel of reality itself. Each tetrahedron can exist in only a small number of possible states, and the state of any one tetrahedron determines the states of others throughout the fabric of the universe. But if a tetrahedron can occupy only one specific state at a given moment, the question naturally arises: who or what determines which state it takes? Many physicists around the world now believe that reality is fundamentally made of information. But what do we mean by information? Information is meaning expressed through symbols, and meaning itself arises from comparison, from the ability to perceive something in relation to something else. And comparison in turn requires choice. In other words, it requires consciousness. Just as the properties of an entangled particle become real only when we measure them, information and meaning can exist only when they are perceived. If this is true, then reality itself may be a product of consciousness. There is, however, another possibility that has captured the imagination of scientists and philosophers alike. The simulation hypothesis, proposed by the Oxford philosopher Nick Bostrom, suggests that the probability we are living in a simulated reality could be 50-50. If we were ever able to prove that our universe is a simulation, how might we go about it? We would have to begin with the assumption that the hardware running the simulation does not possess infinite computational power. If it did, there would be no way to distinguish our universe from one that is entirely virtual. Put another way, only limitations would leave detectable traces. We might never notice any glitches at all, which is why some scientists are searching for experimental ways to force a simulation to expose itself, perhaps by pushing a hypothetical computer with limited computational resources beyond its capacity. At the same time, other researchers argue that every piece of computing hardware inevitably leaves a trace of its existence within the simulated reality it sustains. That would imply a ceiling on how much processing can occur within a given span of time. Intriguingly, our universe appears to contain precisely such a trace. The speed of light remains constant no matter who measures it, setting a strict upper bound that cannot be derived from deeper physical principles. We may have no idea what kind of machine could be running a simulated universe, or what its fundamental characteristics might be, yet one simple observation follows. If that machine carried out a single operation per second, then the size of its memory container for variable space would be on the order of 300,000 kilometers. Perhaps the existence of a light speed limit prevents us from crossing to another galaxy before such a computer has had time to generate it. And that is not the only hint that our reality could be artificial. Films and video games often adopt the viewpoint of their characters to present events from within the story. What we see on the screen and hear through the speakers forms a unified experience that serves no function for the characters themselves. It exists entirely for the observer. If we take the simulation hypothesis seriously, consciousness suddenly acquires a distinct role. It becomes an integrated subjective interface composed of 5 senses. No known natural law, philosophical framework, or scientific theory predicts the emergence of consciousness, nor does it offer an obvious evolutionary advantage. It seems to exist primarily so that there can be experience at all. Yet, experience without clear utility or evolutionary benefit is energetically costly, suggesting it may serve someone else entirely, perhaps an observer or a player. If humanity were ever to discover a method for simulating conscious beings, the probability that we ourselves inhabit a simulated reality would increase dramatically. Physicists at the University of Maryland have already succeeded in simulating a single nucleus of helium made up of 2 protons and 2 neutrons. They suggest that if an atomic nucleus can be simulated today, then within 20 or 30 years, a molecule might follow, and in 50 years, an object measuring a few inches. If progress continues along this trajectory, it is conceivable that within 100 years, scientists could simulate the human brain. The crucial point, however, is that if we truly live in a simulation, we are not scripted line by line because we possess free will. Perhaps the intention was to observe what we would do without guidance, to see what might unfold. The long years we experience could amount to mere minutes for whoever created the simulation we inhabit.